Hello students, in today's lecture we are going to learn about mechanical properties of fluids. NCERT section 9.3 to 9.4. This is disclaimer, learning objectives. By the end of this lecture you will able to understand the fundamental concepts of fluid dynamics including streamline flow, laminar and turbulent flow and the equation of continuity. Apply Bernoulli's principle to analyze fluid flow in various scenarios relating pressure, velocity, and height while solving practical problems involving fluid dynamics. In today's lecture, we are going to cover section 9.3 streamline flow, then 9.4 Bernoulli's principle. So, let's start. So now we will try to understand the principles and behavior of steady fluid flow patterns. This means we will be exploring how fluids like water and air move when their flow is smooth and constant over time. Keep in mind, steady means the properties at any given point in the fluid do not change as time passes. The study of fluids in motion is called fluid dynamics. This is different from fluid statics, which deals with fluids at rest. Fluid dynamics helps us analyze how liquids and gases and move and interact with their surroundings. So fluid dynamics governs everything from blood flow in our circulatory systems to the flight of aircraft. Alright, these are just two examples, but fluid dynamics is essential in many areas of science and engineering. Now, take a moment to look at the historical development of fluid dynamics. Understanding where these ideas come from helps us appreciate how the field has evolved over time. The mathematical foundation of fluid dynamics was first established by Leonard Euler, who created equations to describe fluid dynamics. Alright, or we can say to describe fluid motion. Later, Claude Lois and George Garbiel-Stokes refined these ideas, leading to the Navier-Stokes equation, where we can say which are still used today to predict how fluid behave in different situations. The work of Euler, Navier and Stokes provides the mathematical tools we use to understand and predict fluid motion. These equations are fundamental in physics and engineering, helping us solve real-world problems involving fluids. Now, let's define steady flow. Alright. So, in steady flow, the velocity of each fluid particle passing through a given point remains constant over time. That means if you watch a particular spot in the fluid, the speed and direction of the fluid at that spot don't change as time passes. Look at figure, fluid particles move with respect to time. Alright, and their velocity at point A is v1, velocity at point B v2. So the figure, it shows fluid particles moving smoothly. and each one follows as predictable path. This is what we mean by steady flow. However, steady flow does not mean that the velocity is the same everywhere in the fluid. Alright? Different points in the fluid can have different velocities. For example, fluid might move faster in the center of a pipe and slower near the edges. The important thing is that at each specific point, the velocity stays constant over time, even if it's different from other points. At another point in the fluid, a particle might have a different velocity, but every particle that passes through that point will behave in exactly the same way as the previous one. This means the flow pattern is consistent and predictable at every location. Alright, so in steady flow, each fluid particle follows a smooth path, and these paths never cross each other. This is important because it means the motion is orderly, not chaotic. The smooth and non-crossing paths are called streamlines, and they help us visualize how fluids move in steady flow. Now, let's introduce the concept of a streamline. Alright. So basically, a streamline is simply the path that a fluid particle follows as it moves. At any point along this path, the direction of the streamline matches the direction of the fluid's velocity. Alright, this means if you draw a tangent to the curve at any point, it shows you exactly where the fluid is heading at that moment. So look at the figure here. It shows two things. Alright, there is a figure say 9.7a, a typical trajectory of a fluid particle. B, a region of streamline flow. So if we talk about the first, the actual path is a single fluid particle might take, and second, a region where many streamlines are drawn to represent the overall flow. Alright. So from this figure 9.7, we can say streamlines never cross each other. This is because at any given point, the fluid can only have one direction of motion. So now let's focus on the path of a single particle as shown in figure 9.7a. Alright. So this curve, this one A1, this curve tells us exactly how a fluid particle moves over time. So by following this path, we can predict where the particle will be at any moment, which is crucial for understanding and analyzing fluid flow in real life situations. So particle fluid flow from P to Q. The curve leveled PQ acts like a permanent map of the fluid's movement. It shows us the route of the fluid streams follow of helping us visualize the overall fluid pattern. Alright. Now, now let's talk about the properties of streamline flow. So, streamline flow, also called laminar flow, is when every particle of the fluid follows a smooth path and these paths never cross each other. So, first key property is that two streamlines can never cross. Alright. So this is the first property. So at any point along a streamline, the direction of the fluid's velocity is exactly along the tangent to that line. Look at figure A. At point P, if you want to find out the direction, so draw the tangent here. Similarly, at point Q. Alright. So at any point along the streamline, the direction of the fluid's velocity is exactly along the tangent to that point. So here in the figure 9.7, it shows how streamlines represent the direction of flow at every point. Alright. So here fluids flow orderly. If two streamlines were to interact, then what happened? So it would if two streamlines were to interact, it would mean that at that single point, the fluid would have two different direction of the velocity at the same time. Alright. So if we talk about that point P, so suppose at point P, the two streamlines are cross. So at that point, the direction of velocity is 2 at the same time. That's physically impossible. Alright. So we can say two streamlines never cross each other. Alright. So at at that point, the direction of velocity is at the same time. That's not physically impossible for a fluid, because at any instant a particle can only move in one direction. So streamlines never cross. I hope this is clear. Another important property is that the density of streamlines. So density of streamlines tells us about the speed of the fluid. Where streamlines are close together, the fluid is moving faster. Where they are further apart, the fluid is moving slower. For example, around the narrow part of a river, water flows faster because the streamlines are packed tightly together. In steady flow, the pattern of streamlines stays fixed over time. Alright, this means that if you look at the flow at different moments, the path don't change. This stationary pattern is a key feature of steady or laminar flow, and it helps us predict how fluids will behave in many practical situations. Now, let's talk about an important equation called equation of continuity. So here now we will learn equation of continuity. So consider a fluid flowing through a pipe. Look at figure. All right. Of varying cross section. Here varying cross section means the cross section is different at different points. So at point P, the cross section is this one. All right. At point R, the cross section is changed. At point Q, the cross section is again changed. All right. So the figure 9.7 shows fluid flowing through a pipe that changes in width. All right. So here look at the streamlines. These lines are shows the path that fluid particles follow. So in figure A, in part A, you see a single particle path, and in part B, you see a region where the flow is smooth and steady, which we call streamline or laminar flow. I hope this is clear. So at different points along the pipe, labeled P, R, and Q, the pipes has different cross sectional areas, which we call AP, AR, and AQ. Alright. The fluid also moves at different speeds at these points. which we call VP, VR, VQ respectively. Changes in area affect the speed of the fluid at each point. Now, let's see how much fluid passes through one of these areas. Alright. So, the mass of fluid crossing at area AP in a small time interval delta t is given by the formula uh, rho p AP VP delta t for mass. Alright, or we can say mass is equal to rho p AP VP delta t. Here rho is the density in kilograms per cubic meter, area in meter square, velocity in meter per second, and time in seconds. This formula shows that if the area gets smaller, the velocity must increase for the same amount of fluid to pass through. Alright, now uh, consider fluid flowing through a pipe of varying cross section. Alright, so similarly, mass of fluid delta mr flowing or crossing at AR in a small interval of time delta t is rho r AR VR delta t. Alright, and mass of fluid delta mq is rho q AQ VQ delta t crossing at AQ. Alright, the mass of liquid flowing out equals the mass flowing in holds in all cases. So putting it all together, we get the equation, that is rho p AP VP delta t is equal to rho r AR VR delta t is equal to rho q AQ VQ delta t. This equation is very important. Alright, each term represents the mass of the fluid passing through different sections in the same time interval. Now, let's look at what happens when a fluid is incompressible, meaning its density does not change as it flows. Here, the density at point P, point R, and point Q are equal. Rho P equal to rho R equal to rho Q. Alright. So, equation 9.9 reduces to we have a equation 9.9, that is rho p AP VP delta t is equal to rho r AR VR delta t. Rho g is equal to rho g AG VQ delta t. Alright. So the equation simplifies further to AP VP is equal to AR VR is equal to AG VG. Here A stands for the cross sectional area in square meters. V is the velocity in meters per second. This means that the product of area and velocity is constant along the flow. So if the area decreases, the velocity increases and vice versa. This is the core idea behind the equation of continuity. Now, uh, let's talk about the incompressible fluids. So an incompressible fluid is one where the density, which we call rho, stays constant as the fluid moves. Water is a good example of an incompressible fluid under most everyday conditions. So here the equation of continuity for incompressible fluids, APVP equal to AR VR equal to AQVQ. In this equation, A stands for cross-sectional area at a point in the pipe or channel, and V is the speed of fluid at that point. The subscript P, R, Q just refer to different locations along the flow. This equation tells us that the product of area and velocity is same at every point along the flow as long as fluid is incompressible. So this leads us to a more general relationship. So AV equal to constant. All right. Physical interpretation. When a fluid moves from a wide section to a narrow section, its speed increases. That's why, for example, water flows faster through the narrow part of a river and slows down in the wider parts. This is a direct consequences of the equation of continuity, and you can observe it in everyday life. All right. So we know in narrow sections velocity increases, in wider sections and velocity decreases, explaining why the water flows faster through the narrow part of a river and slower in wide sections. Now we will understand turbulent flow. All right. So now let's look at the what turbulent flow actually means. Turbulent flow is when a fluid moves in a very dynamic and unpredictable way with lots of swirling motions called eddies and vortices. So look at uh, figure shows how the streamlines are irregular and the jet of air creates a chaotic pattern when it hits the plate. This is very different from smooth, steady flow, and it's important in many real life situations like river, rapids, or air moving around a car. So it occurs at high velocities, low viscosities, and in the presence of disturbances or obstacles. All right. Now, uh, let's define laminar flow. Laminar flow is a smooth and orderly movement of fluid where the particles move in parallel layers called without much mixing between them. All right. Look at figure. Here, the streamlines are straight and don't cross each other. This is different from turbulent flow, where the movement is chaotic and the layers mix together. The figure also shows a jet of air hitting a plate, which is an example of turbulent flow, not laminar flow. So, in laminar flow, each particle of the fluid follows a predictable path, moving along well defined streamlines. This means if you were to track a single particle, you could easily predict where it is would go next. It occurs at low velocities, high viscosities, and in the absence of obstructions. All right. Now we will learn Bernoulli's principle. So Bernoulli's principle is one of the most elegant ways we apply the law of conservation of energy to fluids. It tells us that as a fluid moves, the total energy along a streamline remains constant as long as there is no friction or energy loss. Bernoulli's principle was developed by Daniel Bernoulli in 1738. He found a fundamental relationship that links three important properties of fluid: its pressure, its velocity, and its elevation. Now, let's look at the historical context. Understanding where these ideas came from helps us appreciate their importance. So, Daniel Bernoulli was part of a famous family of mathematicians. He lived from 1700 to 1782 and made major contributions to mathematics and physics. His family legacy includes several important discoveries, but Daniel's work on fluids is specifically significant for us today. In his book Hydrodynamica, Bernoulli introduced the idea that energy is conserved in fluid flow. This was a major step forward in physics as it connected the motion of fluids to the broader concept of energy conservation. Remember, this principle is foundation for much of what we study in fluid mechanics. All right. Now, uh, first, let's talk about the physical foundation of Bernoulli's principle. It's important to know what assumptions and conditions we are working with before we dive into the details. We will focus on how fluids move and what factors affect their motion. So consider a fluid moving in a pipe of varying cross-sectional area. This change in cross-sectional area affects the speed and pressure of the fluid at different points. So here, let the pipe be at varying heights as shown in figure 9.9. The figure shows how a section of fluids moves from one part of the pipe to another over a certain time. Look at figure. Both the area and the height change, which means both speed and gravitational potential energy will play a role. Alright, so we will use this setup to explore how energy is conserved as the fluid flows. Alright, so look at figure. Height h1 at point first and height h2 at point second. Alright, now now imagine an incompressible fluid, meaning its density does not change, flowing straightly through a pipe. So take a look at this figure 9.9. It shows an ideal fluid moving through a pipe that changes width. So fluid moves from one section to another over a certain time. This length V1 times delta T and V2 times delta T represent how far the fluid travels in each section during the same time interval. Alright, and this setup helps us visualize how the fluid's properties change as it moves. So as the fluid moves through sections of different widths, its velocity must change. This is because of the equation of continuity. Alright, so which the equation of continuity states that the amount of fluid entering one end of the pipe per second must equal the amount leaving the other end, since the fluid is incompressible. Uh, Alright, so in simple terms, if the pipe narrows, the fluid speeds up. If it widens, the fluid slows down. This relationship is given by A1 V1 is equal to A2 V2. Alright, so to make the fluid speed up or slow down, a force is needed to cause this acceleration. This force comes from differences in pressure in different regions of the pipe. In other words, the pressure is not the same everywhere. It's higher where the fluid slows down and the slower where it speeds up. So the this pressure difference is what drives the fluid's motion and is a key part of Bernoulli's principle. So when a fluid flowing through a pipe from point first to point second with different cross sectional area, all right, A1 and A2, and elevations H1 and H2. Its velocity changes according to the continuity equation. Alright. So according to continuity equation, the velocity of fluid must change as it moves through these sections. Remember, continuity equation is a1 v1 equal to a2 v2. So these velocity changes require forces which arise from pressure difference. All right. So for example, if the fluid speeds up, there must be a higher pressure pushing it from behind and a lower pressure ahead. This is similar to how you need to push harder to get water to move faster through a narrow hose. So Bernoulli's equation quantifies these relationships using energy conservation. All right, it tells us that as the fluid speed increases, its pressure decreases, and vice versa. Now, work energy analysis. So in time delta t, fluid moves distance v1 delta t at point first and v2 delta t at point second. All right. The figure here shows how the fluid travels through sections of different sizes. So work done by the pressure forces at point first, W1 equal to P1 A1 into V1 into delta T is equal to P1 into delta V. At point 2, W2 equal to minus P2 A2 into V2 into delta T is equal to minus P2 delta V. So if we add up the work done as both ends, the total work done on the fluid is the difference between the work at point first and point second. This total work is what actually changes the energy of the fluid as it moves through the pipe. So putting it all together, the total work done is W equals to P1 minus P2 into delta V. This formula tells us that the net work depends on difference in pressure and the volume of fluid moved. Now, uh, if the density of the fluid is rho and mass passing through the pipe in time delta t, is delta m equal to rho a1 v1 into delta t is equal to rho into delta v. Change in gravitational potential energy is delta u is equal to rho g into delta v h2 minus h1. Change in kinetic energy, which is the energy due to the fluid's motion. So delta ke is equal to 1 by 2 rho into delta v, v2 square minus v1 square. So applying work energy theorem, this theorem states that the work done on a system is equal to the change in its kinetic energy plus the change in its potential energy. So W equal to delta Ke plus delta Pe. So P1 minus P2 is equal to 1 by 2 rho into delta V into V2 square minus V1 square plus rho G into delta V H2 minus H1. So we now divide each term by delta V to obtain. So P1 minus P2 equal to 1 by 2 rho V2 square minus V1 square plus rho G into H2 minus H1. So we can rearrange the above terms to obtain P1 plus 1 by 2 rho V1 square plus rho G H1 is equal to P2 plus 1 by 2 rho V2 square plus rho G H2. Now, Bernoulli's equation general form. This equation is fundamental in fluid dynamics and connects the pressure, speed, and heights of a moving fluid. It's named after Daniel Bernoulli. This relationship only holds for steady, incompressible, or non-viscous flows. So P plus 1 by 2 rho V square plus rho GH is equal to constant. Now let's now summarize what we have studied. So for this for studies so far in this section lecture. Fluid dynamics studies fluid in motion with foundations laid by Euler, Navier, and Stokes. Steady flow means fluid velocity remains constant at any given point over time. Streamlines are paths whose tangents show fluid velocity direction at each point. Streamlines never cross each other as it would imply two different velocities at same point. Equation of continuity states that mass flow rate remains constant. Alright. For incompressible fluids, slower velocity in wider sections and fast in narrow sections. So, laminar flow is smooth and orderly, while turbulent flow is chaotic and adage. Bernoulli's principle connects pressure, velocity, and height in a fluid flow. So Bernoulli's equation P plus 1 by 2 rho V square plus rho GH is equal to constant. Alright. Now we have some practice questions. First, water flows through a pipe that narrows from a diameter of 8 centimeter to 4 centimeter. If the velocity in the wider section is 3 meter per second, what is the velocity in the narrow sections? So here you have to find out the velocity in the narrow sections. If water flows through a pipe with cross section area 30 centimeter square at a velocity of 4 meter per second, what is the volume flow rate in meter cube per second? All right. So here you have to find out the volume flow rate. Calculate the Reynolds number for water flowing through a pipe of diameter 2 centimeter with velocity 0.5 meter per second. Given water density 1000 kilogram per meter cube, viscosity 0.001 pascals. In a horizontal pipe, if the pressure at point A is 150 kilopascal and the velocity is 2 meter per second, what is the pressure at point B where the velocity is 6 meter per second? Water flows through a vertical pipe that rises 3 meters. If the velocity at the bottom is 4 meter per second and pressure is 200 kilopascal, what is the pressure at the top if the velocity there is a 2 meter per second? Use rho equal to 1000 kilogram per meter cube and g is equal to 9.8 meter per second square. Alright. So these are the practice questions. Alright. These questions build your concept and improve your problem solving skill. Alright. Thank you for your attention.